happy to be here in Moscow once again. I think it's maybe the 5th time. I don't remember exactly. And it's a pleasure for me. And to take part to this meeting on Vasiliev. So I know Vasiliev since 20 years, I think, because I read his book been translated in Portuguese in Brazil. Very nice book. It's what was prepared some years ago. And I will speak about these 3 main topics: square proposition, power constancy, imagination, which are all related with some idea of Vasiliev, and I've been working on that since many years. So first, I will speak about the square proposition. So Vasiliev criticized the traditional square proposition, explain why it's wrong in some sense. I will explain this again and see how the work was developed after Vasiliev. So just the picture of the square for the people who don't know the square. I guess most of the people know the square. And but I'm using some specific colors. It's easier to represent the square. So this is the basic definition of the 3 notions of opposition that appear on the square position: contradictories, contraries, and subcontraries. So there is a problem discussed by Vasiliev. It's the corner which is called E. Some men are white. Well, if we have a situation like that, we will not say generally we will not say that some cats are black. It would be strange to say that in this situation. Maybe in this case it makes sense. Okay. So what happened is that in mathematics we may use sometimes the quantifier sum as sum and maybe whole. More precisely, in mathematics, this quantifier means at least one. Existential quantifier, as we say nowadays, which appear at the E corner of the square. But in natural language, when we use this word sum, it means some but not all. And this is also the case in empirical science. This is what Vasiliev points out. It means some but not all. So the sum of the square is not good to describe the sum we are using in natural language and in empirical science. So the idea of Vasiliev and other people after him, like the Danish linguist person and the French philosopher Blanchet, is to argue that the triangle is better than the square. Let's see why. For the quantifiers, we will have this blue triangle. Blue because the only relation of opposition we have here is the notion of not contradiction but contrariety. All, none, and some. This is the exact meaning of this quantifier in everyday life. And we have many versions of the triangle. For time, always, never, sometimes. For space, everywhere, nowhere, somewhere. And also for modalities: necessary, impossible, possible. Also for the deontic modalities: obligatory, prohibited, allowed, which are illustrated here with these traffic signs. Well, generally, I mean, these traffic signs, we may find them in Western Europe. I don't know in Russia if it's the same. Maybe. In Brazil, generally, there is only the red one. But we may find, so this is a good picture of this triangle of opposition. We can try to see if it makes sense to have a square of deontic modalities. There are some countries, for example in Switzerland, where we have this over traffic sign for not obligatory. It's not very common. So generally, when we are thinking, we always use something like a triangle, some basic structure of our thinking, much more than the square. When we are thinking, and also for action, because what is interesting about this deontic version of the triangle is it's related with action. Okay, but we can go further on. This was the idea of Blanchet, not just to stay with a triangle of opposition, but to have an hexagon of opposition. And in the hexagon of opposition, we will find back the square. Well, this hexagon of opposition was presented by Robert Blanchet in 1993 in a paper was published in this Swedish Journal of Philosophy. It was published, the paper was originally published in French, sur l'opposition des concepts. And later on, he wrote a book about the hexagon, which is very nice, which is called Structure intellectuelle, Essai sur l'organisation systématique des concepts. The book is not translated in English, but it has been translated recently in Brazil, in Portuguese. So the hexagon, here we have the picture of the hexagon. So in the hexagon we have the blue triangle, as you can see, all, none, and some. And then we have another triangle, which is a triangle of subcontrariety, which is green. And this triangle is built by taking the strong opposition of the three corners of the blue triangle. So we can take the classical negation. Not all, not none, not some. Of course, we can try to think about this, this new notion in a positive way, not only in a negative way. For example, we may have this interpretation. So not none, it means at least one, not all, at least not one. And at the top, not some means all or none. And we have also, Blanchet proposed also some other variation of the hexagon, not only for quantifier, but also for modalities. And this hexagon of modalities is very interesting because we make the distinction between two modalities, possible and contingent. At some point, I decide to use these words as they appear in this hexagon. Of course, we can discuss if this is really the natural meaning of these two words, but there is not really a natural meaning. The idea of contingent here, the definition of contingent in the hexagon, means possible but not necessary, which is in fact generally it's also the meaning of possible in everyday life, because if we say possible, it means possible and not necessary. But here we make the distinction between possible and contingent. So people have started to work on this modality of contingency, especially in Australia. People have been working on that, and also, which is in fact the most natural modalities from the point of view of standard thinking, and also the negation of it, which is at the top, non-contingent. And we also have an hexagon of deontic hexagon. Then we make the distinction between optional and allowed. And at the top, non-optional. The basic structure of the two additional corners are defined by Blanchet as a conjunction at the bottom, and at the top, the disjunction of the two corners. So you can see that in this hexagon we have the square back. We have back the square, and we have two additional traditional modalities. Now we can use this hexagon to think about many concepts. The name of the book of Blanchet is Structure intellectuelle, donc, intellectual structure, essai sur l'organisation systématique des concepts. Because the idea of Blanchet is that this structure, like the hexagon, is a way of thinking about kind of anything, many kind of, it's a basis of conceptualization, of kind of conceptualization. So I have been myself developing different hexagons for different situations. For example, this hexagon I have built for music. I was taking part to a seminar about music, philosophy and mathematics in Paris last year, and I present this hexagon. So we have the basic idea of this hexagon is first to have this triangle, music, noise and silence, and then trying to think in a positive way the three opposite concepts we can find. You can see that at the top, sound seems quite natural because sound is music or noise, in the definition, according to the definition of Blanchet. Here, this is another hexagon about the idea of identity and difference. Identity and difference, strong opposition, which is expressed here in red, but we may have other kind of approximate notion, like similarity, analogy, which appear here on the hexagon. Also, it's interesting to use this hexagon to think about this famous distinction made by Kant. We have two positions in Kant, the distinction between analytic, synthetic, and a priori, a posteriori. And using this hexagon, we can try to see the relation between these two dichotomies. And this gives a nice definition of this famous synthetic a priori and analytic or a posteriori. Also, Blanchet was using the hexagon at the level of metalogic. And we can develop this idea of, for example, Blanchet made a classification of the standard collective of classical logic with the hexagon, and also we can use it for the basic notion of the basic definition of metalogic, of modern logic. So we can classify formulas of given logic in there are 6 situations. Something, formula is a tautology, ontology. There is also the idea of satisfaction, refutation, meaning at the back, at the bottom, mean. Why mean? Because it's a formula that can be true and can be false. And absurdity at the top. And we can generalize this idea also for the relation of consequence. Using this terminology, consequence, satisfaction, refutation, and so on, that maybe it's better to use kind of symbolization. For example, if we take as an example of a theory, here PA, which is piano arithmetic, well, we have these 6 situations which are very famous in modern logic. Before the time of modern logic, people were not thinking really in this way. Now we can see at the bottom a formula K, which is independent of arithmetic. It's a famous result by Gödel, and this other situation, which are the basic definition of model theory. And this classification we have here, we can use it not only for classical logic, but for any kind of consequence relation. And in fact, for any logic, we have this 6 situation. It's really a description of metalogic. Now, I will say a few words about the relation between the square proposition and power constant logic. In 1933, Gödel proved this result that it's possible to make a correspondence between intuitive negation and modal logic S4. We have read this paper by Gödel in this book, Universal Logic and Ontology, and in this book it's a collection of papers which are presented by some specialists. In this case, Professor Itala wrote the paper of Gödel is 2 pages, but she presents the paper in 20 pages. Description. Very important result by Gödel, which is connected with all this theory of translation between logic. Okay. So you can see in this picture, the negation of intuitive logic is impossible in S4. Now, some years ago, maybe 15 years ago, I don't remember exactly, I had the idea to study to consider the not necessary as a negation. And in fact, not necessary is a power constant negation. We can argue that it's a power constant negation. In fact, I present this result here in Moscow like 10 years ago, as far as I remember, during the Smirnov Congress. So I wrote this paper, which has been published here in Logical Investigation, which is called S5 is a power constant logic. And also another paper about the power constant logic Z. This power constant logic Z, if I come back here, the idea is that if we consider classical positive logic, it means logic with conjunction, disjunction, and classical implication. Very simple logic. And if we add to this logic this connective, which appear here in the O corner, which is a power constant negation, so we have just this as an additional connective, it's possible to prove that just adding this to classical positive logic, we can define classical negation and all the modalities. It's a reconstruction of S5, starting only with this connective, so it's quite interesting aspect. Okay, and we can make this full picture if we want to have a better understanding of the modalities and negation. Because in the square of modalities, we don't have classical negation alone. Now, if we want to introduce classical negation alone, we can have this picture using these 3 colors, which represent the free notion of the free opposition of the square. But at first I did this picture, but I didn't like it very much. So I thought it was better to have these 2 additional stars, which is on the left a power complete star, and on the right a power constant star, because we have a power constant negation, and the other one we have a power complete negation. And then we can put together these 3 stars. The first being the classical star of modalities. And when we put together these 3 stars, we go to a 3-dimensional object, something more or less like this famous stellar dodecahedron. Here it's a picture by Escher of the dodecahedron. So when we put together these 3 stars, we have this 3-dimensional object which represents all the relation between modalities and negation. Now, let's come back to Vasiliev. So, Vasiliev used this terminology. This will be the last part of my talk. I will criticize the terminology he is using. Imaginary logic, non-Aristotelian logic. So this terminology was inspired by Lobachevsky, imaginary geometry, non-Euclidean geometry, which also was from Kazan. Well, I'm not sure this is a very good terminology. I mean, of course, the work of Vasiliev is very interesting, but this terminology is a bit confused. I will explain why. First, what does it mean when we when we are facing this expression, non-Aristotelian logic, what's the idea we may have? Well, it's difficult to say, because what exactly is Aristotelian logic? Well, there is syllogistic, it's a basic system, and several ideas of Aristotle. And in fact, we know that Aristotle was not a classical logician. Of course, he was promoting the law of non-contradiction. This is a point that is emphasized by Vasiliev. Sure. So there is the idea of non-contradiction. But at the same time, Aristotle was defending a different negation than classical negation, because he was the initiator of the square opposition, where we have the notion of contrariety, which is not classical, which is a different notion of opposition. It's not classical negation. Nowadays, we can see this as a par-complete negation. And the second point is that Aristotle also was the main inspiration for the development of medieval logic by Lukasiewicz, because this idea of indetermination and maybe a proposition is neither true, neither false. So, in fact, people working in medieval logic, there was this famous logician from Romania, Vasiliev. He preferred to use this expression to speak about medieval logic. He used, his book was written in French, Essai sur la logique non chrysipienne, because it appears that the first to have really put forward the principle of bivalence was Chrysippe, not Aristotle. Okay, so this was my first slides about Vasiliev, about the idea of non-Aristotelian logic. Now the second point is that imaginary logic. Also, I will make a few slides about this expression of imagination here. I think why Vasiliev is using this expression, we have seen yesterday people describing the work of Vasiliev, explaining well, making quotation of his work. The idea of Vasiliev is that imagination, he used this word by opposition to reality. So for him, the imaginary logic is not the logic of reality, it's the logic of something we have imagined in some sense. But the word imagination, if we want to understand better how we develop our thinking, we can try to use imagination in a way which is more precise. That imagination, it's related with images. So it can be concrete images like painting, photo, picture, and so on, and also kind of subjective image, mental image, ideas. And it's difficult to say that to use this word for any kind of idea. Some ideas are more related with image, and some not so much. So, if we can make this distinction between imagination and conceptualization, and we can say that's two different ways of thinking. We can think sometimes in a more imaginative way, and sometimes more conceptual way. When I'm speaking about conceptualization, I'm thinking about ideas, theories like scientific theory like theory of relativity, theory of evolution, and so on. And a lot of theories, we don't have any image to relate with the theory. Especially in modern physics, it's very difficult to have an image of the microscopic world corresponding to the theory. We can say that mathematics, in general, is beyond imagination, because something like zero, Aleph, transfinite numbers, things that we can conceive, but we have no image of these mathematical objects. There is a famous discussion by Descartes about this. Diagram. What is a diagram? Diagram is a polygon with 1,000 sides. Well, we don't have any image of this. This is what Descartes says, because it's too complicated to have a mental representation of this. So this is not here an image of the diagram, but it's an image of Descartes. And we don't have any image of of this object. But in mathematics was used this expression imaginary numbers. Once again, I think it's not a good terminology, because we don't have any image of imaginary numbers. So when people decide, I don't know exactly who, I have to check, who decide to use this expression to speak about imaginary numbers. He was the guy who chose this expression because he wanted to speak about something that we can even create by our mind. But at the same time, we have no image of these numbers. So I don't think we have it's a good idea to call these numbers imaginary numbers. In general, we can say that conceptualization is beyond imagination. We can imagine many things, like a dragon and so on. But even for something which is not mathematical, negation, I will argue now that negation is something which is beyond imagination. Can we imagine a non-cat? Well, we can imagine a cat, we can make a picture of a cat, so it's an image of a cat. Now, do we have an image of a non-cat? No, because non-cat, it's can be many different things, and we cannot represent all these things by a single image. Here are some examples of non-cat: a dog, for example, a car, a cell phone, number 2. So we have a lot of different. This non-cat is something which is very a lot of different kind of objects, and we cannot represent this with an image. Maybe the closest way to represent this with an image is something like that, but it's kind of abstraction. So we can say that non-cat classical negation is something it's related with conceptualization, especially conceptualization of human beings, because it seems that the animals don't have this idea of negation. And it is also something which is very abstract because we cannot represent the negation of a cat, for example. And we can say also that the same about contradiction. Contradiction, we can conceive contradiction in the sense that we can define what is contradiction. For example, in modern logic, it's very easy to define with proposal logic. We say that P and not P is a contradiction. So we have a definition, we have a conceptualization of a contradiction. At the same time, we cannot imagine contradiction. Why? Because, for example, if we want to have an image of a round square, well, this is not really a round square. I mean, it will be very difficult to represent a contradiction. Okay, but at the same time, so I was saying that imagination is not many things like negation, also in science, in physics and so on. We don't work with image. But at the same time, we can still use image. Let's come back to the hexagon. For example, the hexagon is an image. So it's a very symbolic image, but it's a way to think. It's a nice picture, and it's good to develop our ideas. So we can use the image to diagram. It's very useful even in mathematics. So I'm not saying that image are something completely useless, but sometimes we don't have any image. Here we have an hexagon where we have some different kind of logical structure. L3 is Lukács logic, free-body logic. Lk is classical logic, and then we can consider the negation of this logic. The negation of Lk, I call it anti-classical logic, is defined taking the complement of the consequence relation of classical logic. And we can argue that this anti-classical logic is a logic in the same sense that the negation of L3 is a logic. Lukács himself had an interesting idea to develop a refutation system. Refutation system is a proof system that generates all the formulas which are not tautology, for example, of LK. So this is a way to consider this hexagon, to consider that this different structure, logical structure like anti-classical logic is still a logic. And to finish, so a nice picture about the conference we're organizing in Rio de Janeiro next year. So I hope that many Russian people will join us in Brazil, where the temperature is hot here. Okay, thank you.